Section 10.11, Fractals. We call a set in R2 bounded if it can be enclosed by a suitably large circle, and closed if it contains all of its boundary points. Two sets in R2 will be called congruent if they can be made to coincide exactly by translating and rotating them appropriately within R2. If T from R2 to R2 is the linear operator that scales by a factor of S, see the table 7 of section 4.9 that we did previously, and if Q is a set in R2, then the set T of Q, the set of images of points in Q under T, is called a dilation of the set Q if S is bigger than 1, and a contraction of Q if S is smaller than 1. In either case, we say that T of Q is the set Q scaled by the factor S. A closed bounded subset of the Euclidean plane R2 is said to be self-similar if it can be expressed in the form S equals S1 union S2 union S3 and so on, where S1 through Sk are non-overlapping sets, each of which is congruent to S scale by the same factor between 0 and 1. So as an example, we have a line segment in R2. It can be expressed as the union of two non-overlapping congruent line segments. So here's a line segment. It's the union of these two congruent line segments. Well, maybe you could draw them a little bit better than me so that these are actually equal to each other, but it's close enough. I moved them a little bit apart so you could see, but you could line them up so that they're exactly just two congruent pieces of that line segment. In any case, we have K equals 2 because we have two pieces and each piece is half as big as the original, so S equals half. Another example is that a square can be expressed as the union of four non-overlapping congruent squares. Let's determine the values of K and S for this self-similar set. So I'll draw a square and I'll draw the four squares that I could use to make the square, because I could break it up into 4, and these are all supposed to be identical, so again, maybe your drawing skills will be better than mine. In any case, we have K equals 4, and each one is half as big as the original if you go by the length of each of these sides. It's half the length, even though the area is 1/4. We say that S is going to be half. Let's do another example. The set suggested by the figure, the Sierpinski carpet, was first described by the Polish mathematician Wacław Sierpinski in 1882 to 1969. That's when he lived. Let's determine the values of K and S for this self-similar set. Okay, so we have how many pieces? Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Great, so K equals 8. And each one is a scale factor of 1/3 of the original, right? This is 1/3 as long, this is 1/3 as long, this is 1/3 as long as the whole thing. So S equals 1/3. The figure illustrates another set described by Sierpinski. Let's determine the values of K and S for this self-similar set. All right, I've got one over here, one over there, and one over there. So K equals 3, and the length of this guy is half the entire length, right? Each of these is half the length, so the scale factor is a half. The definition of the dimension of a subspace given in section 4.5 is a special case of a more general concept called topological dimension, which is applicable to sets in Rn that are not necessarily subspaces. We denote the topological dimension of a set S by dts. Let's get the topological dimensions of the sets given in examples 1 through 4. So for S, we had a line segment in example 1, and in that case we have dts equal to 1. And for the square, we have dts equals to 2. We consider it to be two-dimensional. for the Sierpinski carpet, we actually consider that to be one-dimensional. This is actually really hard to prove, even though it's difficult to even think about proving it because we gave a kind of a hazy definition of topological dimension in the first place. It's really not even a definition, but it is true that the dimension is 1, and we can kind of imagine it to be true because there's so many holes in the Sierpinski carpet. Right? There's like infinitely many holes that the actual object kind of resembles more, it bears a closer resemblance to lines than to a two-dimensional object like the square. And similarly for the Sierpinski carpet, there's so many different holes that it's basically just considered just a web of lines, just tons and tons and tons of lines, which you could kind of imagine unfolding as one big line. I guess is one way to think about it. So the Sierpinski triangle also has topological dimension 1. And again, very difficult to actually prove that, so we're not going to really talk about it super in depth, but there you go, a couple of random facts. The Hausdorff dimension of a self-similar set S is denoted by DHS and is defined by lnk over ln1 over S. All right, so this is a little bit easier to actually calculate. We can actually get the Hausdorff dimensions of the sets given in examples 1 through 4. So let's start with S, the line segment. And in that case, we had little s given by half. That was the scale factor, and we had 2 different line segments. So k was 2, and therefore DHS would be ln2 divided by ln2. Kind of cool. So that's 1. Okay, how about for the square? Well, then we had s equal to half again, but this time k was 4. We had 4 squares, so that's ln4 divided by ln2, which is 2. How about if we look at the Sierpinski carpet? So in this case, we had s equal to 1/3 and k equal to 8. So we have ln8 over ln3, which is roughly 1.892. So I'll just set it equal to that and dot it. How about the Sierpinski triangle? Well, in that case, we have s equals a half, k equal to 3. So we get ln3 over ln2, and that, again, we're going to have to approximate. So I'll write it out as 1.584 dot. A fractal is a subset of a Euclidean space whose Hausdorff dimension and topological dimension are not equal. Because notice, for the first two, we had 1 and 2, which matched dt. But for the second two, they did not match because I bullied you into thinking that the dt would be 1 for Sierpinski carpet and Sierpinski triangle, which does not match the DHS. While I'm here, maybe I'll add the lines for this table. Okay, let's keep going. So a similitude with scale factor s is a mapping of R2 into R2 of the form txy equals s times cosine minus sine sine cosine xy plus ef, where s, theta, e, and f are all scalars. Let's consider the line segment s connecting the points 0, 0 and 1, 0 in the xy plane, and we'll find similitudes whose union is s. So I will draw this. Let's see. So let's say over here would be the origin. And I'll put 1, 0 over here. And I need similitudes whose union is S. So I need two chunks over here. One will go from 0 to a half, and one will go from a half to 0. So I'll make this guy T1 of S, and then this other guy can be T2 of S. So S will be those unions. I could write T1 explicitly as applying to X, Y. Well, I need to just take the entire thing and shrink it by a scale factor of a half, and then this entire big piece will just end up over here as T1. So I'll just take half of 1, 0, 0, 1 applied to xy. So whatever xy was, just take, half of 1, 0, 0, 1 to that. Cool, so now let's do T2 of xy. And in this case, I need to shrink it down so that the entire thing is shrunken down to become T1, but then I need to move it over, right? I need to start over here. So I'll start by shrinking it down half 1, 0, 0, 1 times xy, and then I'll translate by adding half to the x coordinate. And then together we'll get S if I take the union of these two guys. Let's consider the unit square u in the xy plane as shown in the figure. We'll find similitudes whose union is u. Okay, so I'm going to draw what I'm going to do here. So how about make this my x-axis, y-axis. Let's break up the square. So here will be 1, 1, and here's 0, 1, and 0, 0, and 1, 0. So then what I could do is shrink the square down so that it's 1/4 of the size, and that'll get me my T1 of u, similar to what we did before. So this would be at 0, half, and that just takes this transformation of x, y, and it's just half of the identity applied to xy. So here's xy. Okay, good. And then I would like to, how about move it over here? So I'll shrink down and then move over, and then I'll get this guy. So that'll be T2 of u. And I have to move it over half, so on the x, so T2 of xy is equal to half of the identity applied to xy, and it has to be translated by half in the x direction, similar to the previous example. For T3, how about I go shrink and then translate up this time? So this will give me T3 of u. So I'll take T3, apply it to x, y, and we'll start by shrinking. And then after we shrink, we'll translate this time in the y direction, so 0, half is what we'll add. And then we got, just to wrap things up with T4. So T4 of x, y is, again, the shrinking part. And then we have to translate it up and across, so I'll do half for both x and y. And then u, the square, is the union of these transformations. So it's T1 union T2 union T3 union T4. How about we consider the Sierpinski carpet over the unit square u of the xy plane and find similitudes whose union is S. So it looks like we could again take the entire thing and then shrink it down and then just translate. So we'll have 8 different of these little shrunken versions of it, and they're translated in various places depending on which one we want to do. So the first one we won't translate at all, and the second one we'll translate maybe to the right by 1/3, and then you could go to the right 2/3, etc. So in general, those transformations can be denoted by Ti of xy equal to 1/3 to shrink, 1, 0, 0, 1, then apply that to xy and translate by some EI, depending on where we want to put it. And we'll have to do that 8 times, so I'll set I equal 1, 2, 3, all the way through 8. So let's explicitly write out what the EIs should be and the FIs. So that should be 0, 0, 1/3 for the first one. We'll translate, won't move it up. For the second one, we'll keep going. We'll do 2/3 this time. Again, not move up yet. Then how about we move up 1/3? And then we could translate 2/3, move up 1/3. Why not? We could move up 2/3. And we could move to the right 1/3, up 2/3. And then last one would be at 2/3, 2/3. So then S would equal the union of T1s, union T2s, union T3s, and so on, all the way through T8s. How about we next consider the Sierpinski triangle S fitted inside the unit square u of the xy plane as shown in the figure, and find similitudes whose union is S. So it's the same essential coordinate system and the same plan. We'll write T1 of xy equal to the first shrunken one to the origin, so we won't translate yet. And then we need T2, so we'll shrink and we'll translate. So half, 1, 0, 0, 1 applied to xy, and then how about we move to the right half? And then for the last one, there'll be T3 applied to xy, and that'll be half, 1, 0, 0, 1 applied to xy, and then we'll translate up a half. So we only needed 3 of these guys, that's great. So we have S equals T1 S union T2S union T3S. If T1 through Tk are contracting similitudes with the same scale factor, then there is a unique non-empty closed and bounded set in S in the Euclidean plane such that S is equal to the union of all those guys. Basically, this theorem says that we can always find these you can always take these unions and build S out of it. Furthermore, if the sets T1 through Tk are non-overlapping, then else S is self-similar. Let's use similitudes to construct the Sierpinski carpet, starting with the unit square in the xy plane. So I'll start with the unit square. So here's y, here's 0, 1. I need to go to 1, 1. So here's 1, 0. Here's 0, 0. And I'll call this S0 for our starting square. And then what I'll do is I'll put a smaller shrunken square inside of it. Oops, could do a little better, okay. And I'll call it S1 when I put the smaller square inside. It's my first iteration, essentially. Oh, this is X, okay. So I'll now do this a third time, putting smaller squares inside. So I have to keep S1 and then essentially keep going, putting in smaller squares. Okay, so this would be S2. And then I could do S3. I don't know if I can actually draw it, but I'll try. Let's see. So I gotta do my big square in the middle. I have to do my big-ish squares, or my medium squares. And then I have to do a whole bunch of small squares around them because I keep shrinking. And this is going to take some time, but it's okay. Okay, so it didn't come out as good as yours will, I'm sure, but that's the general idea, and then it just keeps on going like that, and you get the Sierpinski carpet. Let's use similitudes to construct the Sierpinski triangle, starting with the arbitrary closed and bounded set S0 in the figure. There's nothing special about the square. You can actually make these shapes out of any starting shape is the idea. So this we'll call S0 for my 0th iteration, and then for S1, let's see if I can draw these S's. Okay, so there's 1, 2, and 3, and we'll call that S1. And then for the second iteration, I have to do 3 smaller ones, so I could do better than that. 1, 2, 3, and I need 3 for the next one. Oh, that one didn't come out good. And you can kind of see where this is going maybe now. I'll do it for one more iteration for S3. So let's see if I can, oh boy, this is a challenge. Yeah, maybe I'll just make them a little bit sloppy. That's okay. Once again, I'm sure yours will come out better than mine, but you get the idea. How about we consider these following two similitudes, T1 and T2, and let's describe the actions of these two similitudes on the unit square for various values of theta. So let's draw the unit square. Now let's see what happens. So here will be 1, 1, my unit square u, put 0, 0, and 1, 0. And then what we have to do is it looks like we have to shrink but also rotate by angle theta, and we have to translate. Okay, so we could do this. Let's do it. We'll draw this out. So here's x and y, and I'll shrink it to a half. This is T1, oops, T1 applied to u. So here's 0, half. Here's 0, 0. And here's half, 0. And then I need to rotate it. Okay, we can do the rotation now. It should be through an angle theta, and it should translate by 0.3. So I'll translate it over here. This is going to be 0.3, 0.3, and here will be my angle theta at which I rotate. So I'll end up with something like this. And this should be a half. Okay, so this is T2 of u. All right, so I need to basically apply both of those different similitudes. Okay, the general idea for different values of theta. How about I first do it for, let's say, a 60-degree theta. So you start with, how about a bunch of little squiggles, and they kind of rotate and shrink and rotate and shrink and rotate and shrink. So it's by 60 degrees, so something like this. And I'm sure you will have nicer squiggles. I believe in you. And how about I put the next one over here to keep making them smaller because they keep shrinking. Not so easy, actually. And I have to rotate while I shrink. Let's see if I could even do this. I mean, you can almost imagine. Good enough. How about for theta equals 30 degrees? So then in this case, it's not going to rotate by as much. It's a little bit less pronounced. So just rotate them a little bit. Let's see if I can, again, rotate and shrink, rotate and shrink. Should be kind of curling inward. Pretty hard to see. Should actually be a little bit more slow than this, but that's okay. And then if theta equals 0 degrees, then it's not rotating at all. So it's just a straight line shrinking down from 0.6, 0.6 all the way to the origin. An affine transformation is a mapping of R2 into R2 of the form Txy equals ABCD xy plus EF, where ABCDF are scalars. So now we have a name for this sort of thing.